What is up, my impossible integrals? We are going to talk about techniques of integration. Any Calc 2 student can tell you that they probably have a love-hate relationship with integration. What we're going to do is we're going to try to figure out techniques to figure out how to even approach an integral. So we're going to talk about 1, 2, 3, 4, 5 main ways of integrating. So we're going to have substitution, or some people call those U subs. We're going to talk about by parts integration. We're going to talk about partial fractions. We're going to talk about trig identities. And we're going to talk about trig subs. Yes, there are more. There are very subtle, sort of trickier ways of integrating things, but these are the main 5 that you'll encounter in a Calc 2 course. So we're going to talk about them, but what I want to do is I want to talk about them through the lens of we already know these. How do you figure out which to use? If somebody hands you an integral and they say, hey, if you don't solve this integral in the next 5 minutes, the world's going to end, how do you figure out how to solve that integral? That's the hard part, figuring out what to do. So what I'm going to do is I'm going to put some integrals up here on the paper, and we're going to figure out how to integrate them. So this video is going to assume that you know these 5 techniques right here, or that you're at least somewhat comfortable with them. And if not, what I'll probably do in the near future is make videos outlining how to do each individual one. And when I make those videos, I will definitely put those in the description. If you don't see them in the description, they're probably not made yet. But, so I'm going to assume that we know how to do these 5, and I'm going to hand us some integrals, and we're going to determine which to use. All right? So, let's look at this integral right here. The integral of x squared e to the 5x with respect to x. So, somebody hands us this integral, and they say, integrate it. So what I'm going to do first is I'm going to put all the integrals that I'm going to do up here, and I'm going to first write down what technique they are and how I know it's that technique, and then later on in the video I'll actually solve each of them. But I'll try to make this as efficient as possible. So when I have a problem like this, the first thing I'm going to think is either substitution or by parts. I'm not going to think partial fractions, because partial fractions is usually when you have rational expressions to integrate. So polynomial on top, polynomial on the bottom. So this e to the 5x, this function right here, sort of takes partial fractions out of the running. Trig IDs and trig subs, we'll talk more about those later, but there's nothing trigonometric about these. And especially with trig subs, there's something that happens with trig subs. As you may recall, you have like an x squared plus an a squared, or x squared minus a squared, things like that. You have some sort of sometimes a square root involved, but not always. So this is really not a trig sub type thing. So my mind, when I look at this, automatically goes to either a U sub or by parts. So how do I figure out which it's going to be? Usually, and I'd say like 95% of the percent of the time, if it's a U sub, then the thing that's inside of another function has a derivative that is something outside of it. And that may be vague and confusing, but here's what I mean. Usually if this is going to be a U sub, this 5x up here, I'm going to differentiate. And if I'm going to use a U sub, the derivative of 5x, which is 5, would cancel all the x's from whatever's out in front. And that actually doesn't happen. If this were reversed and this were an x squared here and this were 5x, the derivative of x squared is 2x, and that x would cancel with the x that was right here. So when you have the derivative of something being something on the outside of it, that's how you know you use a U sub most of the time. Not all the time, but most. And so that sort of takes U subs out of the running. So this is probably going to be a by parts integral. All right, later on in the video, I'll actually solve this integral, but for now, we're going to label that as by parts and move on. All right, so how about this integral right here, number 2? What if we needed to integrate 6 sine of 4t cosine of 4t with respect to t. How would we even approach this integral? Well, there's actually two ways. All right, so by parts, one could argue maybe it's a by parts integral because there's multiplication here. That's one way that you know it's probably maybe a by parts. Perhaps there's some sort of trig identity that we learned in trig to do it. Not a trig sub, because again, it's not like an x squared plus a number squared or a number squared minus x squared or anything like that. So trig subs we can sort of cross off the list right now. So maybe trig identity, maybe partial fractions, maybe by parts. I'm sorry, not maybe partial fractions. Let me back up. That's not a partial fractions because, again, it's not a rational expression that we're trying to integrate. It's not a polynomial on top, polynomial on bottom. Maybe this is even a u sub. Okay, so I'm going to write u sub here because the derivative of cosine of 4t is plus or minus the derivative of sine t. And I worry about the signs later if it's going to be a plus or a minus. But anyway, so the derivative of something is something else in this problem that would cancel out. So u sub is a perfectly good choice for us, as is trig identity, because if you remember your trig identities, you should recognize something about sine of theta, cosine theta. We'll talk about that in a bit. So these are two perfectly good possibilities for this problem. As a matter of fact, number 2 can be solved with both of these. I'm going to go back up here and circle by parts, because that's going to be what we're going to use for number 1. And as a matter of fact, for number 1, it is a by parts integration. And before I move on, I just want to stress that number 1 is by parts because the thing out in front, this x squared, with derivatives will eventually go away. The derivative of x squared is a 2x, the derivative of 2x is 2, the derivative of 2 is 0. And that's a pretty good indication that the thing that you're integrating is going to require a by parts integral. Alrighty, so that's that one. I'm also going to do number 3 here at some point, the integral of x times the square root of x squared minus 4x plus 4. I'm sorry, plus 20. My apologies, with respect to x. Now, let's go through. Substitution, possibly a u sub, but that's off the list because x squared minus 4x plus 20 has a derivative of 2x minus 4. And that 2x would cancel with this x, but there's also this pesky 4, this pesky minus 4 hanging around. So it's not a pure just 5x or 2x or something like that that's going to cancel that x. So as far as a u sub goes, the derivative of the inside bit isn't completely constant multiple aside the outside. This is a 2x, which is good for u sub, but then a minus 4. If this were just a 2x derivative on the inside, then it would cancel with that x, and I know I'd probably want to use a u sub. By parts integration seems reasonable because I have multiplication here, all right? And this x is something that goes away. Partial fractions off the list because it's not a rational expression. It's not a polynomial divided by another polynomial. Trig identity, well, this isn't a trig function at all, so we're not going to use trig identities. But trig sub is actually how we're going to do this one right here. And the reason is this isn't x squared minus a squared, but I can complete the square on the inside here, and it's going to be the square root of something plus or minus something squared. So I can actually complete the square here, and that's going to do it. All right, and then we'll see how that works. But one of the reasons I might want to avoid by parts, remember, if something on the outside disappears with differentiation, that's a good sign that you're going to use by parts, because the derivative of x is 1, derivative of 1 is 0. So that's a pretty good indication. But I'm also going to have to integrate this thing right here. Remember, by parts requires a derivative and an integral, and I don't want to integrate the square root of x squared minus 4x plus 20. I mean, we're actually going to do it with the trig sub, but it's not abundantly clear how we're going to do that in this problem. So while it may be by parts, we're going to tackle this one with the trig sub just because it's going to give us practice with completing the square. And then we're going to do number 4. Number 4, we are going to integrate 8x minus 8 over x squared plus 8x plus 15 with respect to x. So let's go through the list. A u sub is promising. If I call this bottom u, that's going to be x squared plus 8x plus 15. And if I differentiate u with respect to x, that's a 2x plus 8. But the problem is, this derivative isn't a constant multiple of this thing right here. If this were like an 8x minus 8 or 16x minus 16 or something like that, if this derivative were a constant multiple of that right there, it would cancel with a u sub. So that's hopeful, right? That's a pretty good indication that u sub is the way to go. Unfortunately, that doesn't happen, so u sub is out of the question. By parts, I certainly don't want to have to integrate this bottom thing all by itself. If I called u 8x minus 8, I would have to integrate 1 over x squared plus 8x plus 15, and that's not really going to help me out too much. All right, it's doable, but partial fractions is probably the way to go here because I have a rational expression and a u sub didn't work. If I have a rational expression, I automatically think u sub. But since my u sub didn't work, in my mind, I automatically go to partial fractions. At the same time, since it's rational, I'm not going to worry about a trig sub at this point. If I'm going to do partial fractions, I'm looking for rational expressions like this. First degree polynomial on top, second degree polynomial on the bottom, partial fractions all day long, so I'm going to attempt those. All right, so hopefully just this discussion right here helps you figure out maybe some strategies for figuring out integration. Now we're actually going to go through and solve these 4 integrals completely to see how the biparts and the u subs and the trig identities all work here. So here we have number 1. We have the integral of x squared e to the 5x. We've determined that u sub wouldn't work because you would probably call u equal to 5x. And a derivative of u with respect to x is 5, and that's not going to do anything with this x squared out here. When you do a u sub, you want to replace all of your x's with u's. You're not going to be able to get rid of that x right there. So u sub is sort of out of the question. So we're going to do biparts integration. All right. Remember, the formula for biparts is the integral of u dv is equal to u times v minus the integral of v du. And the hard part about biparts integration is sometimes, one, remembering where you are in the whole problem, but also, two, figuring out what you're going to call u and what you're going to call v. And most of the time, the thing that disappears with differentiation, such as x squared, is usually the thing you want to call u. So I'm going to call u equal to x squared, which means that a derivative of u with respect to x is 2x. Right? I'm going to need a du in my formula. I have a u. And that means that I'm going to call dv this other thing right here. dv is e to the 5x with respect to x, which means when I integrate both sides of this thing, I get that v equals e to the 5x over 5, like so. Now, where's that over 5 coming from? Well, that's just the basic u sub. So this whole thing is a biparts integral with a u sub right there, because when I call u equal to 5x, the derivative of u is 5, and that's going to appear on the bottom right there. All right, so we're going to fill out all this information. This integral is equal to u, which is x squared, times v, e to the 5x over 5, minus the integral of v, which is e to the 5x over 5, times du. Now du, when I cross multiply, is 2x dx. So when you do biparts integration, you always have an integral in the answer. And so I'm going to write this as x squared e to the 5x over 5. I'm going to go ahead and pull these constant multiples out. Minus 2/5 times the integral of x e to the 5x with respect to x, like so. Now, This may seem frustrating because, oh man, I still have this x e to the 5x here. But all that means is we're going to do by parts once again. Because now I already used u and v just to be on the safe side so I don't confuse myself. I'll call u1 equal to x, which means that a derivative of u1 with respect to x is 1. I'll call dv equal to e to the 5x dx, which means that v is, once again, e to the 5, oh, and let's be careful, I'll call it v1, e to the 5x over 5, like so. And so this by parts integral has another by parts integral inside of it. And again, this v1 is a simple u substitution, and integral of e to the 5x is e to the 5x divided by 5. And if you're not convinced of that, take a derivative of v1. Those 5's will cancel and you'll get dv1 right there. So this is equal to x squared e to the 5x over 5, because we're already done with those, minus 2/5 times this integral that we're doing by parts here, which is u1 v1 x e to the 5x over 5 minus the integral of v, which is e to the 5x over 5 du1. So when I cross multiply this dx over, I get 1 times dx, which is dx. And so let's go ahead and distribute this 2/5 here and here. So I get x squared e to the 5x over 5 minus 2 over 25. I almost forgot what 5 times 5 is. X e to the 5x plus 2. I'm going to go ahead and pull that 5 out. Boom, right there. 2 over 25 times the integral of e to the 5x with respect to x. And I just noticed that you didn't see any of that because it wasn't on the screen. So I'll go ahead and go through this again. That's handled. That's done. I distribute this negative 2/5 here and to here. So 5 times 5 is 25, negative 2x e to the 5x. And then these two negatives make it positive 2. These two 5's I'll multiply together to give me 25, integral e to the 5x with respect to x. And for the third time in this problem, I need to integrate e to the 5x with respect to x. We know what that is. That's e to the 5x divided by 5. X squared e to the 5x over 5 minus 2/5 x e to the 5x plus 2 over, since there's gonna be this over 5 bit right here, 5 times 5 times 25 is 125, and I don't need my integral anymore. We get x squared e to the 5x over 5 minus 2/5 x e to the 5x plus 2 over 125, because I'm integrating this 5 right here, so I get an over 5. 5 times 25 is 125, e to the 5x, and then I add my arbitrary constant c, because I'm all done with my integral. And if you want to check if this is the answer, you would differentiate this thing right here and make sure that you get that right there. So again, how do we know that this is by parts? It's the multiplication of two things, and one of the things disappears with differentiation, and this is a transcendental function. So it's easy to integrate this thing. That's why I called this dv. It's very easy to compute the integral of e to the 5x. As a matter of fact, I did it 3 times in this problem, so there we go. All right, next on the list is this integral right here. We called it number 2. I'm actually going to do it 2 different ways. First, I'm going to do a u sub. All right, so u sub. The reason is I'm going to call u cosine of 4t. That's that piece right there. A derivative of u with respect to t. Remember, a derivative of sine is positive cosine. Derivative of cosine is negative sine. So I get negative sine 4t, and then by the chain rule times the derivative of the inside bit, which is multiplied by 4. And so if I solve this for dt, dt equals du over negative 4 sine of 4t. All right, so what do I get? This becomes the integral of 6 sine of 4t times, calling this thing u right here, so u times dt, which I've solved for with my substitution right here, to be du over negative 4 sine of 4t, like so. And again, this is how you know that you probably want to use a u sub, because the derivative of the thing, the derivative of u, appears right here, and they will cancel, like so. And so 6 over 4 is 3 halves, so I get negative 3 halves times the integral of u with respect to u. Doesn't get much easier than that, because that's by the power rule, negative 3 halves u squared over 2 plus an arbitrary constant. And then I go ahead and plug that value for u back in, and I get negative 3/4 times cosine squared of 4t plus an arbitrary constant, like so. And that's it. Why did I put so much space there? I have no idea. But that's solving this integral using a u substitution. All right. Now, the other way that I would do this would be a trig sub, because recall, so let's call it this, method 2. Trig sub. Not trig sub, trig ID. We're going to use a very common trig identity that you should have learned in trig, which is that sine of 2 theta equals 2 sine theta cosine theta. When you see sine and cosine multiplied together, you should think double angle identity for sine. And that's what I have right here. All right? So I'm going to make this right here look like that right there. So I'm going to write the integral as 3 times, remember we want that 2 out there, 2 sine of 4t cosine of 4t with respect to t. All right? Now, I need to make these match, and so therefore theta is 4t. And if theta is 4t, then that means that 2 theta must be 8t, like so. And so this becomes the integral of 3 times my double angle, sine of 8t with respect to t. All right? So I make this substitution right here. This is a double angle identity, and that's easy to integrate now. Now, it's a simple u sub. So what I'm going to do is I'm going to call u equal to 8t. So a derivative of u with respect to t is 8. This is the exact same u sub I did on number 1 when I just sort of flew through it with the e to the 5x, because what I get is that dt is du over 8, like so. Do my cross multiplication, and so I get 3. Remember, we can always pull constant multiples out of integration, times the integral of sine u times du over 8. Pull that 1 over 8 out, we get 3/8 times the integral of sine u with respect to u. And then we just need to remember what the integral of sine u is. So in my head, I always got to go through it. The derivative of sine is positive cosine, so therefore the derivative of sine, or I'm sorry, the integral of sine would be negative cosine. So this is negative 3/8 cosine of u. Now let's just go ahead and recall what u was. I've done my u sub, so that's just 8t plus an arbitrary constant c. And there we go. And then that begs the question, is this answer right here the same as that answer right there? And bonus points for the person to show that that is the same as that right there. I won't go through it right now, but you can actually verify that these are the exact same answer. They don't look like it, but they are. All right, that brings us to number 3. I chose to do number 3 in this video against my better judgment, because I think it's going to be quite the beast. But I claimed earlier that I'm going to use a trig sub on this one. Now remember, in trig subs, when you have things that look like this, you make these substitutions. Trig subs are very, very elusive to students because there's no trigonometry here. There's no sines or cosines or anything like that. Yet all of a sudden we start making these things, these substitutions. So it's rather counterintuitive. Also, what is it about this that would make me think trig sub? Because this doesn't even look like that, right? And the reason really is that I can make this a perfect square under here and cross my fingers and hope that something magical happens, right? And sometimes with integration, I'm going to make this point again, hopefully later if I remember, but the thing with integration is you get good at it by practicing it, and in that practice you have to keep failing. You have to keep getting the wrong answer. And what that does is it's sort of like an electric fence where if you start to veer off the wrong path enough and you'll get shocked, you'll learn to not go that way eventually. And there's nothing I can really say or do that'll teach that. You have to do 1,000 of these problems and keep getting shocked by investing tons and tons of time into doing these problems and getting them wrong time and time again. And that's just what I did in Calc 2. And I became rather proficient at doing these things, mainly because I knew how miserable it was to go down the wrong path and get it wrong and to sort of hit a dead end. So that's really what I should have started this video off by saying. And this is one of those problems where you can maybe try it a couple different ways. It's easy to see that a U sub is not going to work, and I went over that reason a little bit earlier in the video when I introduced problem number 3. But let's just go for it. This doesn't look like a perfect square, but I'm going to make it a perfect square by completing the square. So remember how completing the square works. I'm going to do the, I'm going to take the b, the middle coefficient, which is -4. I'm going to divide it by 2, and I'm going to square it. So I get x squared minus 4x plus 20. I'm going to take -4. I'm going to divide it by 2, which is -2, and square it. So I'm going to add that. Now I can't just add 4 out of nowhere. What else I have to do is subtract 4 as well. And the whole point of completing the square is I can group this and this thing that I just added together, and that's guaranteed to be a perfect square. So I get the integral of x times the times the square root of x minus 2 squared. That's how these underlined bits become a perfect square. And then 20 minus 4 is 16 with respect to x. Now this does look like one of these things. As a matter of fact, it looks like this middle one right here, because I have a variable thing squared plus an integer squared, 4 squared, right? So what I'm going to do is I'm going to call x minus 2 equal to 4 tangent theta. I chose to do this problem because it's not just an x squared right here, it's a variable thing squared. So if it's x squared plus a squared, whatever that thing being squared is your substitution, like so. Now I'm going to go ahead and just substitute all that in there. So when I substitute x, I'm not just substituting x, I need to add that 2 over, right? So I'm not going to call that 4 tangent theta. This is going to be x, which is 4 tangent theta plus 2, because that's what x is. All right. Now remember, when you do these things, you also need to differentiate x with respect to the new variable theta. So when I differentiate, it doesn't really matter where this 2 goes. I'm differentiating with respect to theta. 2 is constant no matter what. The derivative of any constant is 0. The derivative of 4 tangent theta is 4 secant squared theta. And so when I want to replace my dx, which I need to do at some point right here, that's going to be 4 secant squared theta times d theta. All right, let's continue with this though. This is the square root of x minus 2 squared, so that's 4 tangent theta squared plus 16 times, and then I just ran out of room, but luckily I ran out of room right next to that thing. So I'll just say times that. And I'm going to do the good mathematical thing of rewriting everything nice and neat so I don't lose myself. 4 tangent theta plus 2 times the square root of, let's go ahead and write this as 16 tangent squared theta plus 16 times 4 secant squared theta d theta. Ooh, this is getting interesting, isn't it? I can factor a 16 out, and underneath the square root of 16 times the square root of tangent squared plus 1. So this becomes 4 tangent theta, don't forget your parentheses, plus 2 times the square root of 16 times the square root of tangent squared theta plus 1 times 4 secant squared theta with respect to theta. Not only is this a trig sub, or a trig ID problem, this is a trig sub problem, but I'm also going to use my trig IDs because remember that tangent squared theta plus 1 equals secant squared theta. And the nice thing about that is I'm taking something that's added under a radical, replacing it with something squared under a square root. Those will cancel. Square root of 16 is 4. So I get the integral of 4 tangent theta plus 2 times 4. Now, when we studied these trig subs, these trig IDs, there's this whole business about you don't have to worry about the absolute value when you compute the square root. So I'm not going to go into that. Again, I'm going to assume that you know all this stuff. Really, the point of this is to talk about how you know which to use and when, which I guess I talked about in the first 10 minutes or so of this video. And now I'm just solving integrals for the fun of it because I like solving integrals. So we get that right there. All right, 4 times 4 is 16. I'm going to go ahead and pull a 16 out. Times the integral of 4 tangent theta plus 2 times secant cubed theta d theta. Because secant times secant squared is just secant cubed. All right, we're getting there. I'm going to go ahead and distribute this secant cubed here and here. So I'm actually going to get two integrals. I'm going to get 16 times the integral of 4 tangent theta secant squared theta plus 16 times the integral of 2 secant cubed theta with respect to theta. So I have these two integrals. Let's go ahead and label them I1 and I2, because I'm going to actually handle these separately. So let's first talk about I1. How do you handle I1? Well, first, 4 times 16, I believe, is 64. And you'll also notice that I made a mistake. That should not be secant squared, that should be secant cubed. But what I am going to do is write this a little bit differently. I'm going to write tangent theta, and I'm going to break up these three secants being multiplied together. I'm going to write this as secant theta times secant squared theta, and I was a bad mathematician and I didn't distribute my d theta, which I'll do right now. All right, so we're just handling this integral right now. We'll worry about I2 in a little bit here. So the reason why I broke this up is because remember that the derivative of secant is secant tangent. So the derivative of a thing appears in that problem. So if I call u equal to secant theta, the derivative of u with respect to theta is secant theta tangent theta. And so therefore d theta, the thing that I'm eventually going to want to replace in this u sub integral, is equal to du over secant theta tangent theta. So what does this integral turn into? I get 64 times the integral of tangent theta secant theta times, I called this secant right here u, so therefore this is u squared, times d theta, which is du over secant theta tangent theta. And that's the whole point of the u sub, because secant theta tangent theta, secant tangent theta, blah, 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 you know what I mean. You get that right there. Cross those off, and we get 64 times the integral of u squared with respect to u. And that's pretty darn simple. you get 64 over 3 u cubed plus an arbitrary constant. I'll call it C1 for I1 because I'm doing integral 1. And then what was u? U was secant. And so this is 64 over 3 secant cubed theta plus C1. This is I1 right here. All right? And now we talk about I2. So I2 is equal to, there's a 16 times 2 in there, right there, so that's 32. So I'm not worried about that 32 really. What I'm really worried about is this secant cubed theta with respect to theta. All right, how are we going to handle that? Well, so we're actually going to do this by parts, and it's a different kind of by parts, which is why I chose it. So here we go. What we're going to do is we're going to call, let's see, we need to by parts, so we're going to call u equal to secant theta. I'm going to break this up once again into secant and secant squared, which means that a derivative of u with respect to theta, remember the derivative of secant is secant theta tangent theta. That means that dv is going to be secant squared theta. I've chosen this for dv because it's easy to integrate. The integral of this thing is tangent theta. So this becomes 32 times uv, so secant theta tangent theta, minus the integral of v, which is tangent theta, du, which is secant theta tangent theta. Cross multiply that d theta over. Boom. There we go. So we're getting there. We have 32 secant theta tangent theta minus 32 times the integral of secant theta times tangent squared theta d theta. Now you might be wondering how to handle this thing. Well, I'm going to use another trig sub, and I believe we already used it in this problem, as a matter of fact. Tangent squared theta plus 1 is secant squared theta. So I want to get rid of this tangent theta. I can write it in terms of secant theta. And so tangent squared theta is secant squared theta minus 1. I'll put that in a box because that's not an answer, but that's a trig sub that I'm about to use. Remember, that's one of the Pythagorean identities from trigonometry. So we get 32 secant theta tangent theta minus 32 times the integral of secant theta times secant squared theta minus 1 with respect to theta. Now I'm going to go ahead and distribute this secant theta here. So I get that's equal to 32 secant theta tangent theta minus 32 times the integral of secant cubed theta. And I'm going to go ahead and distribute this here and here to make two separate integrals. And so I get that times d theta minus a negative, so plus 32 times the integral of secant theta d theta. All right? Now, what does that give us? Right here, at this point in the game, we should recognize secant theta. All right? What is the integral of secant theta? This is equal to, this should be, at least when I learned it, we just memorized the integral of secant theta. So I'm just going to use that for this problem right here. All right, so this is 32 times natural log of secant theta plus tangent theta, like so. All right, and that 32 is included with that right there. What about the secant cubed theta? Well, that's what we've been doing this whole time. So the reason why I like this problem is because I'm calling I2 this thing right here. And I2 makes another appearance within itself. So remember, this is equal to I2 right here. And as a matter of fact, this is minus I2 right here. So what I can do is I can add this I2 over, and all my integration goes away. I get 2 I2 equal to 32 secant theta tangent theta, and then plus 32 times natural log of secant theta plus tangent theta, like that. And hopefully you can see what's about to happen. I have no more integrals. I actually just solved it algebraically because I treated the integral of secant cubed theta with a 32 out front like an algebraic object. And so I can divide both sides by 2, and I get that I2 is 16 secant theta tangent theta plus 16 times natural log of the absolute value of secant theta plus tangent theta. And then plus C2, because I'm done with my integral. So the whole integral that I've been trying to solve this whole time is I1 plus I2. And so the integral at hand is, it has an answer, because I'm actually done with all of my integration. We said that I1 was, well, let's write this. So the answer is I1 plus I2. I'll just start a new page here. So what is that? That is equal to, we solved I1 up above, that was 64 over 3 secant cubed theta plus C1, like that, plus 16 secant theta tangent theta plus 16 tangent, well, not tangent, Max, come on, natural log of secant theta plus tangent theta. I just love these trig functions so much, plus C2. I have an arbitrary constant, I'm adding an arbitrary constant, and so we get this equals to 64 over 3 secant cubed theta plus 16 secant theta tangent theta plus 16 natural log, not tangent, of the absolute value of secant theta plus tangent theta plus an arbitrary constant. Ta-da! But wait, there's more. We did not have a problem that had thetas in it. We had a problem that had x's in it. Remember, we made a substitution. We knew that x minus 2 was equal to 4 tangent theta. So when you do these these trig subs, you have to undo them as well. You can't have thetas in your problem because your problem didn't have thetas in it to begin with. Theta was a construct of your own. And so let's divide both sides by 4. We know that tangent of whatever theta was is x minus 2 over 4. So remember what tangent is, back from trig. We got a right triangle right here. Tangent is opposite over adjacent. So this is x minus 2, and that's a 4. And so I'm probably going to need the hypotenuse at some point. And so that's going to be, we'll call that h. H squared is x minus 2 squared plus 4 squared. All right. And so that's x squared minus 4x plus 4 plus 16. Hey, that should look familiar. That had something to do with what we had to begin with in this problem, right? This is h is equal to the square root of x squared minus 4x plus 20. Check out the original problem that we had. We integrated this thing with multiplied by x. So that's my hypotenuse right there. And so I'll write that down. That's the square root of x squared minus 4x plus 20. And so if this is theta right here, I can go ahead and substitute every single one of those secant thetas and tangent thetas with what I have right here. Right? Tangent theta is x minus 2 over 4. Secant theta is hypotenuse over adjacent. Right? So let's go ahead and do that. We have 64 over 3 times secant cubed. So secant cubed is the square root of x squared minus 4x plus 20 divided by 4 cubed plus 16 times secant theta, which is the square root of x squared minus 4x plus 20 over 4. Hey, that 16 and that 4 are going to cancel. That's exciting. Times tangent theta, which is x minus 2 over 4. Hey, 4 times 4 and 16, those are going to cancel. All right. And then what else do we get? We get plus 16 natural log of the absolute value of secant theta, which is the square root of x squared minus 4x plus 20 over 4, plus tangent theta, which is x minus 2 over 4. Like that. All right? And then there's a bunch of stuff that cancels because this is 4 cubed down below. 4 times 4 is 16 times another 4 is 64. That's actually going to go away. You have 16 over 4 times 4, which is 16. So there's just a bunch of stuff that cancels. The c doesn't cancel because that's still in there, but a lot of other things don't. I'm going to finish up my radical right there. You got some division happening. There's a denominator of 4, so that would be minus natural log of 4. Lots of different things that you could do with this problem. I'm not going to go into them. Just understand there's a bunch of simplifying that you could do. If you're to do this problem and look in the back of the book might have a different answer. Doesn't mean you're wrong, it just means that you haven't done your simplifying as much as they have right there. So I'm just going to go ahead and box this. Call that good, because really the whole point of this video is to figure out how to get to the end. We've gotten to the end. The rest is just details with simplifying. And then we have this last problem right here. It's going to be a partial fraction decomposition, as we discussed, because I can't really call the bottom here u, because I'm not going to get a multiple of 8x minus 8 to cancel the thing up on top. So I'm going to use partial fraction decomposition. And once again, there's a bunch of details about partial fractions, like if your denominator has an x squared plus something, then the top doesn't have an x or a constant, it has a ax plus a constant. A lot of details. Again, I'm going to assume that you know all those details or that you could remember them. I'm probably going to do not only a partial fraction integral video at some point, but just partial fractions in general, because that's actually a really important concept in math, especially if you go into differential equations and you do Laplace transforms. Partial fractions are really important. So what I'm going to do is first, forget the integral sign. Let's just write 8x minus 8 over, let's factor this bottom right here. This bottom factors quite nicely because 15 is 5 times 3. 5 plus 3 add up to 8. So I get x plus 3, x plus 5, like that. All right, so I'm going to do a partial fraction decomposition on this. So I'm going to have some unknown constant over x plus 3 plus some other unknown constant over x plus 5. Now I would like for these things to equal one another. Well, this right-hand side needs a common denominator of x plus 3 times x plus 5. In order to bring them together. And I wrote that backwards. That's cool because multiplication is commutative, as we all know. And so this right here is going to be a times x plus 5. Again, x plus 5 divided by x plus 5 cancel, leaving me with a over x plus 3 like I started with. That's going to be a b times x plus 3, like that. The x plus 3's would cancel, leaving me with b over x plus 5 like I started with. But I don't want to cancel them because I want to use those new factors to bring these things together. So I get, let's distribute this a here. Let's distribute this b here. I get ax plus 5a plus bx plus 3b, all divided by x plus 3 times x plus 5. So we want these two things to equal. They now have the same denominator, so I need to make sure that their numerator is equal. And so 8x minus 8 has got to equal, well, let's look at the x components here. There's a coefficient of 8 sitting out in front of my x. And the coefficients that sit out in front of my x here are ax and bx. So the coefficients are a and b. We'll get to that in a bit. The constant coefficients are 5a plus 3b, like so. So when I want to compare these things, I'm going to factor out an x from here, a plus b times x. Here's my constant coefficient, 5a plus 3b. And if I have any hope of these things equaling one another, then this a plus b had better equal 8, because it's a thing times x, a thing times x. Those two things had better equal one another. Okay, so I want a plus b to equal 8. At the same time, these constant coefficients right here, these had better equal negative 8, because if it's minus 8 here, it's got to be a minus 8 right there. And so 5a plus 3b needs to equal negative 8. And what do I have here? Something from algebra. We have a system of equations. 2 equations. We have 2 unknowns. We could do substitution. We could do elimination. We could toss this into a matrix and row reduce it. Bunch of different ways we can solve this right here. I'm going to assume once again that we've done this before, so we know all 3 of those methods. And so I'm going to use the one that I would choose here, which would be elimination. What I'm going to do is I'm going to multiply the top equation and the bottom equation by just the top equation by negative 3, because I want a negative 3b to cancel with that positive 3b right there. Just a personal preference. So don't forget to multiply everything up top by negative 3. So I get negative 3a minus 3b equal to negative 24. And I get positive 5a plus 3b equal to negative 8. Like that. And when I add these equations together, positive 3b minus 3b are 0. I get 2a equal to negative 32. And so a has to equal, divide both sides by 2, I get negative 16. So, in my partial fraction decomposition, I'm going to have a negative 16 sitting up on x plus 3. And what about b? Well, I know that if a is equal to negative 16, let's take either of these 2 equations. I'm going to take a plus b equal to 8, because that seems simpler. Negative 16 plus b has to equal 8. We just found out that a has to be negative 16. If I add 16 to both sides, I get that b equals 24. So that's the magical coefficient sitting up on top of the other part of my partial fraction decomposition. And so let's recall what we're doing. We have the integral of 8x minus 8 divided by x squared plus 8x plus 15, like so. And that equals a over x plus 3. That's what we were trying to do. We were trying to break this up. So we have negative 16, the integral of negative 16 over x plus 3 plus b, which we found to be 24, over x plus 5. And now these 2 things are rather easy to simplify and to integrate, because these are both u subs. Call u x plus 3, call u x plus 5. The derivative of each of those u's would be 1, and so it's a natural log, and so it's just a basic u sub. And there's not even any coefficients that you have to chase around, because it's a 1x right there and a 1x right there. And so I'll just go ahead and say this is equal to negative 16 natural log of the absolute value of x plus 3 plus 24 times natural log of the absolute value of x plus 5. Don't forget your arbitrary constant, like so. And there you go. That is the integral of 8x minus 8 divided by x squared plus 8x plus 15. Now there are some problems for you to practice. I'm going to put the answers down below in the comments. And as far as answers go, I'm going to assume that you can actually solve these integrals once I tell you how to do them. Again, the whole point of this video was to throw some integrals at you and have you come up with strategies and ways of figuring out what method you use. So if you need help with biparts or u subs or partial fractions, that's going to be another set of videos. But for right now, look at these integrals and figure out what you would do, what method you would employ to solving these integrals. I'm going to put those answers down in the comments. Don't forget to like this video. Don't forget to subscribe to this channel. Don't forget to tell your friends. Don't forget to wash your hands. Don't forget to wear your masks. Don't forget to call your mom and say that you love her. Thanks for watching. I'll see you next time.